Precalculus 8.6. Here's the next section after 8.5. This is a continuation of what was in 8.5, so the stuff we were concentrating on there. Complex numbers and the geometry of complex numbers. So we talked about the simple geometrical nature of complex numbers when thinking of them as vectors. If we can think of them as vectors, we could think of them with magnitudes and angles and addition, subtraction, multiplication, and division. Were pretty simple to carry out, which I don't know if I remember. Yeah, we did do a division problem. This is going to be a continuation of that, and what we're going to be concentrating on today are raising numbers to a power, complex numbers specifically, so how to raise numbers to a power and how to think of them geometrically, and then we're going to think about taking roots of complex numbers, and if we know how to take roots of complex numbers, we can solve equations with powers being involved. So we'll start off with a power for complex numbers. So there's a couple of things we want to remember. When we multiply two complex numbers. So we can call this Z1. We can call that A plus BI. And we can also say that that's equal to a phasor, R cosine theta plus I times sine theta, and that's if R is equal to square root A squared plus B squared, and then tangent of theta is equal to B divided by A. So I call that Z1. So we're also going to consider a second complex number. We can call that C plus D times I, which I put a little multiplication sign in between them. I didn't do that for BI, so you just multiply B and I. So in this case, D and I. So this would also equal to, so I'm going to call that R1 theta 1. So this is R1 theta 1, and that's also equal to R2 cosine theta 2 plus I times sine theta 2. So there was an easier way to write this, if you guys remember. There's the CIS way, so R1 CIS theta 1, and this would be R2, and I forgot parentheses there, CIS theta 2. So I had said earlier that mathematicians came up with this simplification of cosine plus I sine. That's what the CIS stands for, cosine I sine. How do I multiply these two? So if I multiply Z1 and Z2 together, the shortcut, you multiply the moduli. So R1 and R2 get multiplied. So the two moduluses, which moduli I think is the proper plural form of that. So R1 times R2. And then this is going to end up equaling to CIS of, you add the two angles, theta 1 plus theta 2. So those two will get added to each other. That's for multiplication. If you wanted to divide them, Z1 divided by Z2 is going to equal to, you divide the moduli, so R1, R2 get divided, and then it's CIS of the subtraction. So if it's Z1 on top, so it's theta 1, then minus theta 2 in that particular order. So these were the two formulas that we ended 8.5 with. So those are the two major things you need to know for 8.5. So for 8.6, it's these two as well. Or sorry, for 8.6, we're going to build on these two. And what we're going to build on top of that would be the power formula. So let's say, for example, if I wanted to square Z1. So Z1 squared. Well, anything squared is itself multiplied again with itself. So Z1 squared is Z1 times Z1. So this is going to equal to, well, in this case, it's R1 CIS theta 1 multiplied with itself, R1 CIS theta 1. So that's an R1. Okay, so those two are getting multiplied. So we follow the rules on how we multiply two complex numbers. And again, you just multiply the two modulus for these two. So that's R1 times R1. And then times, when you're multiplying two complex cosine I sine functions, it's going to be CIS, and you add those two. So theta 1 plus theta 2, which you can simplify, by the way. That is R1 squared CIS 2 theta 1. So theta plus theta is just 2 theta. So then here's our formula for squaring a complex number. So if I wanted to square Z1, or if I wanted to square a complex number, it's equal to the square of its modulus times the complex exponential function of twice its angle. So 2 times its angle. This is the power formula, which we can extend it to higher level powers. Z1, and let's say for example I don't want to talk about a specific power, I want to generalize it. Let's just call that n, where n is some number that's bigger than 1, or it could be 1 as well. 1, 2, 3, 4, 5, 6, and so on. So those are natural numbers. If that's the case, r1 to the nth power, so you raise its modulus to the nth power, and then you multiply theta by the value n, so it's going to get multiplied. So that's an n tuple, it's going to be n tupled. So CIS n theta 1. So if that were 3, it's 3 theta 1. If that were 5, it's 5 times theta 1. In this case, the previous case where that's double, or if that's a square power, so then you double the angle. So this is the general formula, and that's what we have here. And this is one form of de Moivre's theorem. I don't even think that's de Moivre's theorem. De Moivre's theorem is how to take roots, not powers. So I'd have to double check on that. So I think they're misnaming that. It's probably the case that he's the one that studied this at this level, but that's not the final form of his work there in this area. So when you are multiplying or raising some phasor to or some complex vector to some power n, it's the modulus raised to the power times the CIS function of the n-tuple of the angle, n times theta. That's the major formula that you need to know. So we'll look at example number 1 and put that into practice. So they're going to be slightly jerks about it, and here they gave us the exponential form in, and of course you can't answer back to where I can hear it, but what form did they write this thing in? That form is not in what we call polar form, it's written in rectangular form. They're going to want the answer in rectangular form as well. So it's going to look like this. It's some horizontal value plus I times the vertical value. So that's in rectangular form. Remember, rectangular is two linear coordinates that are perpendicular to each other, like an x-axis and a y-axis. That's rectangular form. So those are rectangular coordinates because you can draw rectangles with a particular set of horizontal numbers and a set of horizontal vertical numbers. All right, so as opposed to what's the other form? The other form is polar. Polar is where we're talking about distances and angles. So it's going to be like a curved type of coordinate grid. Instead of a straight rectangular coordinate grid or a linear coordinate grid, it's going to be curved. And it's going to be circular. So the curves are going to be circles. All right, so this is in rectangular form. So I'm going to go ahead and say that that's A, this is B. And remember, when you're trying to find out what those x and y coordinates are, or those horizontal and vertical components are, if you want to think of it as a vector, then you want to separate the number I. I is just a place marker. I tells you that it's vertical, not horizontal. So I tells you it's on the y-axis, not on the x-axis. You ignore the I. So A is square root of 2. And B is also square root of 2. And if you remember, there are formulas, which if you're really, really good at the unit circle, you can already tell what angle that's referring to and what quadrant that's in. So take a look at it really quick and at least try to figure out what quadrant that number is in. There's an x-coordinate and a y-coordinate. Which quadrant is it going to be? So the way you want to think about this is both of those x and y coordinates, or A and B, have positive values, and if they're both positive, that should be quadrant 1, you should have thought. Not only that, they have the same value, square root of 2, and also square root of 2. So the x and y coordinates are equal to each other. What kind of angle is that going to be? So you can think about that for a little while. And you should think that that's a 45-degree angle. So if the x and y coordinates are the same, x equals to y, we're talking about the line with a 45-degree angle through the origin. So I'm already guessing. So I'm going to go ahead and put it out there. Theta, I think, is 45 degrees. Now, I don't want to look like a basic math student. You can call that pi over 4. 45 degrees in radians. So if I want to look a lot smarter, I'm going to do this in radians. So I'm going to go ahead and do that in radians. Pi over 4 is the same as 45 degrees. So anyway, what else am I looking for? I need r and theta. So r, there's a formula for it. R is a squared plus b squared, or x squared plus y squared. X and y, a and b, same idea. Okay, so what is a? A is square root of 2. I got to square it. So there's a square root, and then I have to square the value of a. That's just 2. Same thing with b squared. B squared is just 2, because b is square root of 2. So when you square root, those go away. The square roots go away, that is. And you're left with just what's called the argument or the radicand. So in this case, it's just 2. So we have square root of 2 plus 2. In this case, that's square root of 4, and we get 2. So then my phasor, in this case, I'm going to call that z, by the way. Z, as a complex number in polar form, is 2 cis pi over 4. And I'm going to graph that. Let's take a look at what that would look like on a graph. And remember I said pi over 4 is 45 degrees, so this is pi over 4. And then we're going to be 2 out this way. So 2 from here to here, the origin. That's the distance between there and there. And this right here, square root of 2 and square root of 2. From here to here. So I'm drawing a, what is that, a right triangle? That's the beauty of rectangular coordinates. That's why rectangular coordinates are useful in the first place. We can draw a bunch of right triangles and think of distances in terms of right triangles. So that's what that number looks like. The number is the point here. So that's the number z. Or at least if you want to think of it as a vector, which if I thought of this as a vector, that's the terminal point. This is the initial where the origin is at. Or that's not the origin anymore because we're not talking about an xy coordinate grid now. We're talking about a complex number space. So that's the number 0. So the origin on the complex diagram is actually the number 0. So it's no longer the origin. Now that's actually 0. That's literally 0. Okay, so what are they looking for? Write the answer in rectangular form. Find this number to the 5th power. So all of this I'm saying is z. That's before the 5th power stuff. So I would like to find out what z to the 5th power is then. That's what they're looking for. So that's the actual problem itself. So what is this equal to? So I can write it out. That's 2 cis pi over 4, and then that's raised to the 5th power if I want to stall a little bit. But there's a formula for it, which we wrote up over here. So the formula is if I want to raise some complex number to the nth power, generally speaking, then you raise the modulus to the nth power, and then you just take n times the angle. So in this case, this is going to equal to 2 to the 5th power cis 5 times pi over 4, which we can simplify. That is, well, what's 2 to the 5th? 2 times 2 times 2 times 2 times 2 is 32. Hopefully we knew that. CIS, well, 5 and 4 don't reduce, and pi's along for the ride, so this is just 5 pi over 4. What quadrant is that thing in, 5 pi over 4? That's in the 3rd quadrant. So that's 45 degrees past 180 degrees. That's 225 degrees, if I remember correctly. Hopefully you have your unit circle handy, and you can verify 5 pi over 4 is on the unit circle in the 3rd quadrant, 225 degrees. All of those should be the same thing. So there's my answer, z to the 5th, which I would very much love to box, but there's a problem if I box it. What's the issue if I close that box off? What's this in? This is in polar form, also known as trigonometric form. That's not the form they want it in. So what form do they want it in? They want it in rectangular form. I have it up there underlined. So what's rectangular form? Rectangular form is where we actually evaluate cosine plus I sine of the angle 5 pi over 4 and distribute the modulus 32, so that way it looks like what it started off with in here. So I want it to look like this, with a x-coordinate plus I times the y-coordinate. So then I got to figure out, well, we'll just write it out. 32, this is going to be in parentheses cosine of 5 pi over 4, that's what that stands for, plus I times sine 5 pi over 4 is what that stands for. So that's what the cosine I sine stands for, or that's what the CIS stands for. So what we would like to do next, use the unit circle to evaluate 5 pi over 4 for cosine, or sine and cosine for 5 pi over 4. So those are both negative square root of 2 over 2, if you remember, because that's a 45 degree angle, but in the 3rd quadrant. So square root of 2 over 2 for both of them, with a negative sign on both of them, because it's in the 3rd quadrant. X and Y are both negative in the 3rd. So that's 32. Square root of 2 over 2, negative, and then minus I square root of 2 over 2. So let me double check because I tend to make a lot of mistakes when it comes to minus and plus signs, and it looks fine. Next step, last step, you distribute the 32. So that square root of 2 isn't going to be able to mix with the 32. You could just write them next to each other, but nothing is going to happen. It's the division by 2 on the bottom, the 1/2 or the 2 on the bottom in the denominators, that will reduce with the 32. 32 divided by 2 reduces to 16. So that's going to be negative 16 square root of 2 minus I times 16 square root of 2. And normally the way that we do this, and there's no set way to do this. Usually when there's a square root involved, square root is at the very end, and I don't like the I first if there's a square root, so it's kind of weird. I have like 3 different ways of doing this, and it depends on what the situation is. So negative 16I squared root of 2. You can write the I first, you can write the I last, no big deal. No big deal whatsoever. So that is the number z to the 5th power, the one that they wanted at the beginning, where I let z equal to this. This was z. So that's how you take a complex number to a power, or raise it to some power bigger than 1. So it's pretty simple. The only thing is, because they gave me the number in rectangular form and requested that the answer needs to be in rectangular form, there was a bunch of transformation. So really the major mathematics is done from here to here. So those 3 lines right there are where all of the new mathematics comes from. So the old mathematics is to change this number into trigonometric form, and then to change this number back to trigonometric form, or sorry, back to rectangular form. So we started off with something rectangular, we worked in polar form or trigonometric, and that was easy to work with, and then you got to change it back into rectangular. So that's the hard part about this, in my opinion. Unless you forgot your unit circle, but I can't really help you there. You can't forget your unit circle, or how to use it. That's bad if you forget how to use that. Okay, so now we're moving on to roots. So how do you go backwards? So forwards would be taking a root, multiplying a number with itself, then going backwards. So what number do I multiply with itself to get this number? So we're thinking backwards. So roots are a little bit more complicated. So here's how we do this. So let's say we have some complex number, and I'll just draw one that's in the first quadrant. So let's say that's x, and that's y. So let's say I have a complex number that looks like this, and let's call that z is equal to a plus b I, or ib. So this is a here, and this is b here. And that forms a right triangle here, and that's actually a rectangle, which is why we call this rectangular coordinates. Okay, so that has an r and a theta. So r is from here to here, and it has a theta. So you want to think backwards. Let's think forwards first. If I square that thing, you double the angle. So I'm going to double the angle, but maybe in a different color. Let's do blue. So that way this is theta also. I'll write a little theta in there somewhere. Hopefully you can see it. So there's a theta there, and this is stretched out this way. So it depends on how big the value of a is. If a is bigger than 1, square of a is going to be bigger. So, or we could think of r. r is being squared. So if r is bigger than 1, then the square of r is bigger than r. So it's going to be the square of r, so r squared. And then that angle from here to here is 2 theta. So that's a visual representation of what's going on between z and z squared. So this number out here, that one is z squared. So z has an angle and a modulus. The modulus gets squared when you square it, and then the angle gets doubled when you square the number. So there's a bit of a rotation when you're squaring. Now think of z as some other number. Let's call that w. So think of w as the end result squaring z. So then z is also a square root. So if w is equal to z squared, then z squared is a square root of w, thinking backwards. So let's say, for example, if I square 2, I get 4. Then I say that 2 is a square root of 4. I don't say it's the square root of 4, because we know that there's another square root. The other square root would be what, negative 2? Yeah, so 2 and minus 2 are the square roots of 4. Every real number has 2 square roots. So sometimes, or you might think that that's not true, but it's actually true if I extend my roots to complex numbers. So every real number has 2 square roots. There's only one number for which that's not true. And hopefully you know what number for which that's not true. For 0, the only square root of 0 is 0. There's no plus minus on 0. But let's say, for example, negative 4 has 2 square roots, plus or minus 2i, if you remember. Positive numbers have 2 positive square roots. Negative numbers have 2 complex square roots, stuff like that. 0 only has itself as a square root. So to go backwards, what's the mathematical or what's the geometrical process to go backwards if you have the square and you want the square root? You cut the angle in half. So to find the root, you divide the angle. So theta gets divided by 2. So if you squared by doubling the angle, you're going to square root by dividing the angle by 2, cutting it in half. And then you're also going to take the square root of r for the new modulus. So because we squared the modulus to find the new modulus, to go backwards, you square root that thing to find the original modulus. So you square root r, and then you divide the angle by 2. So there's going to be a bit of a generalization. If I say that w is equal to z to some nth power, then z is equal to the modulus of w to the nth root, and the angle theta is going to get divided by n, if we're talking about the angle. So you take the nth root of the modulus of w, and then you divide the angle, the argument of w, by n. So whatever that root is. So if that were like a cube root, a third root, then you take the third root or cube root of r, and then you divide the angle by 3. So that's going to be the next theorem. So this is the initial. So what we would also call the principal value. And there's going to be n minus 1 more of them. So if n was 5, this is one of them, the principal value, and then there's going to be 5 more. So if you remember, if we're taking a square root, there's 2 of them. So you would find one of them by doing this, by cutting the angle in half and then square rooting the modulus, and you'd find one of them. Then I'd have to find the other one, and that's done geometrically. Now, if this were a 5th root, then we find one of them using this procedure by cutting the angle into 5 pieces. So cut the angle to 1/5 of its original size, and take the 5th root of the modulus, and you only have one of the 5 total answers. There are 4 more answers that we're going to find. So what I'm going to go ahead and do is we're going to practice with very simple ones first, and then we'll do some tougher ones. And by very simple ones, I mean even simpler than the one here in example 2. So I'm going to call this part B for example 2, and I'm going to add a part A before that. So part A for example 2, I'm going to move this over to the side. Find all square roots of, you know what, I want to make that part C. I'm going to do 2 of them. So let's do an easy one. Z equals, let's say, 64. So 64, I like 64. So find all the square roots of 64. And you already know the answer, or at least I hope you do. There's 2 of them. So I'm going to give you some time to think about it. So look at that, Z is equal to 64. What are the square roots, plural, square roots of 64? So you should be thinking 8, and what's the other one? Negative 8. So 8 and negative 8. So how do we get the negative 8? Well, we understand where we get the negative 8 from, because if I take negative 8 and I square it, I get a positive 64, because negative times a negative is positive. Let me have you forget that Forget about the negative. So only think of the positive. So let me have you think of this geometrically. Where do I plot 64 on the complex plane if this is the real part and this is the imaginary multiple? So x and y. So in this case, we're graphing z is equal to x plus iy. Well, in this case, x is what, 64? Y is 0. If it's real and positive, it's on the right side of the x-axis. So it's on the x-axis at 64. And it's not on the, so there's no y coordinate to it. So it's on x-axis at 64. So that's how we graph a positive number, in this case positive 64. So then we also want to find out what the square roots of this number are. So we know one of them, and it's 8. So let me go ahead and draw 8. 8 is somewhere all the way back here somewhere. So because you square 8 and it's 64 and it's a large number. So 8's all the way back there. I'm going to zoom in on that. I'm going to zoom in more. So let's see if that makes sense with regards to the definition or the procedure for finding the roots. So to find a square root of a complex number, you square root the modulus. In this case, what's the modulus of 64? How far away is 64 from 0? It's 64 away. So it's a modulus of 64. What's the angle on 64 though? Because it's on the positive x-axis, the angle 0. So in polar form, 64 is 64 CIS 0. That's what that looks like in polar form or trigonometric form. So 64 is literally a modulus distance of 64 and an angle of 0. Positive real numbers have a 0 angle. So positive real numbers have a 0 angle. So we think of them as just phasors or complex vectors with a 0 angle. So they're really boring. So no angle. So real numbers are just no angle whatsoever, unless we're talking about a negative number. So what's 8? 8 is 8 CIS 0. That's what 8 equals. So the real number 64 is 64 CIS 0. The real number 8 is 8 times CIS 0. So is there consistency with the square roots, the ones that I have here posited, and then the procedure to find square roots? You square root the modulus. So what's the modulus of the previous? 64. You square root the modulus, which is 64, you get 8. The angle, how do you find the angle of a root? You divide, if it's a square root, you divide the angle by 2. But what's 0 divided by 2? You still get 0. So there's no inconsistency there, so it works. It works just fine. So 64, when I square root its modulus, I get 8. And when I square root the angle, it goes from 0 to 0. So we're stuck on the positive x-axis, we stay on the positive x-axis. So no inconsistencies there. How do I find the second square root? We already know the answer to it, and we already know it's negative 8. But let me have you forget about that for now. Think of 64 again as a phasor. 64 CIS 0. What I'm going to do is I'm going to tweak this a little bit to see if I can find a trick for finding the other one. This is the trick that we do. Take the angle 0 and replace it with something that's equivalent, 360 degrees. So let's go around 360 degrees. Or we're trying to drop the basic use of what's it called? Degrees. So it's going to be 2 pi. Think of that as 2 pi. 2 pi is a full circle. 2 pi and 0 are practically the same thing because CIS is periodic. So why did I do that? Follow the same procedure. Take the square root of 64. So I'm going to take the square root of z. I'm going to call that z. Square root of z then, if I play by the same rules, square root of 64, CIS of 2 pi. And what do? We divide that by 2 because we're talking about a square root. So what's CIS 2 pi divided by 2? Well, first off, square root of 64 is 8. CIS 2 pi divided by 2 is pi. So what we've done is we've used this trick to find a second square root. And where's that at? 8 CIS pi. So it's a modulus of 8, so that means it's 8 away from the origin, in this case 0, but it has a rotation angle of pi. So 8 away, angle of pi. And pi is 180 degrees, which if I started off on the x-axis, we land back at the x-axis after a rotation of pi. However, since we're on the left side now, and it has a distance away of 8, that's -8 on the x-axis. And was that supposed to be the other answer? The other answer was -8, and again, we found another consistency. So in this case, that's actually going to be the way that we're going to find all types of roots, not just square roots. We're going to rewrite the angle initially, so the first angle that we found. So we're going to do the procedure and find the first angle, first modulus, and then we're going to add 360 and then divide that by whatever the root value is, and do that over and over until I find all of them. So in this case, we had a square root. We're only finding 2. So our 2 roots of 64, so the 2 square roots of 64, so I'm going to call it z is equal to 64, are 8 and -8, which this was literally 8 with an angle of 0, and this one is 8 with an angle of pi. So that's 0, and I can write parentheses. So that's the geometrical reasoning behind the 2 square roots situation. So the reason being, it's because there are 2 angles that when you take the 0 position and divide it by 2 distinct angles, you get back to the 0 position. So 2 pi and 0, when you divide them by 2, 2 pi and 0 will give you the same position at the beginning. You divide those 2 by 2, and you get those 2 square roots. If you keep on adding more 360s to this, or more 2 pi's to this, you're going to get either 0 or pi, something equivalent to those 2. So they're going to be coterminal to the 2 that we already have. So that's part A. So these are my 2 answers. So I'm going to make this a little harder. Let's try to think of this exact same situation, but I'm going to make it a little bit more abstract. So let's say part B, and you're gonna do this just fine. You're gonna be just fine with this type of an example. Find the roots. I'm gonna call them square roots, and I'm gonna assume I don't know all of them, but the idea is I think there's gonna end up being 2. So find the square roots of z, and let's have a little fun with this. Z equals to, let's say, I'm trying to think, 1/2 plus square root of 3 over 2i. And you might be looking at this and thinking that's crazy. How do I find the square root of a complex number? It's super easy if you think of it geometrically using the same procedure. So you have to change it to polar form to make it easy. Think of it as a vector with an angle and a direction. I can't do this unless I know what the angle is and what the direction is. So we go with the direction. Direction theta is going to equal to, well, I don't know. We're talking about this is equal to r cosine theta plus I times sine theta. So maybe I can find r first. R is the easier one. R is equal to the square root of x squared plus y squared, which I have both x and y. So x squared and y squared. So I would like to square 1/2, so that's 1/4. I would like to square square root of 3 over 2, so that's going to be 3 over 4, and add them. So just double check that. 1/2 squared is 1/4. Square root of 3 over 2 squared is 3/4. And you get 4/4 underneath the square root, which is square root of 1. Square root of 1 is 1. So that means the modulus is just 1. So really this is just cosine theta plus I sine theta. So we're talking about something that's in the first quadrant. So I might want to use the formula for theta that we defined out over there. Theta is equal to inverse tangent of y divided by x. I could use this. Well, we actually defined it by saying that tangent of theta is equal to y over x. But if we're in the first quadrant, I could take its inverse no problem. So we're talking about theta equaling to the inverse tangent of, well, you take square root of 3 over 2, and you divide that by 1/2. If you remember law of the sandwich, it's a while back, tangent inverse of, that's going to be square root of 3. The 1/2s go away, the 1 on the bottom, you can disregard it completely, and you're left with the square root of 3, which survives. So what is the inverse tangent of the square root of 3? So if you're looking at your unit circle, I might not want to take it that far. So if you remember, inverse tangent or tangent of theta is equal to sine divided by cosine in that particular order. So sine is square root of 3 over 2, cosine is 1/2. What angle are we talking about? You should know that that's pi over 3, 60 degrees. That's where I got that from. So I thought 60 degrees, and you could take 1/2 of 60 degrees and it's 30, which is pi over 6. So that's the reason why I chose this. So I'm doing a lot of work just to find out what this is in polar form. So that's 1, and the angle is 60 degrees, or cosine pi over 3 plus I times sine pi over 3. That's what we want to find the square roots of. So I'm going to graph that. Call this x, call this y, and we're talking about a 60-degree angle with a radius of 1. So this is 1/2 plus square root of 3 over 2. So this right here would be 1/2, and this is square root of 3 over 2. And this is, of course, a 60-degree angle, or pi over 3 radians. So I would like to find the square root of that. So what is the square root of z? Square root of z is going to equal to the square root of the modulus 1 times CIS of half of the angle. So that's 1/2 times pi over 3. In this case, square root of 1 is 1, so it still has a modulus of 1. Pi over 3 divided by 2, or 1/2 times pi over 3, is equal to pi over 6. It's 30 degrees. So that one's 30 degrees. So then, that's my first square root of z, which I'm going to graph that one as well. So we can graph the original. So call this x, this one y. The original looks like this. Pi over 3. The new one, half that angle. Same modulus out though, so it's supposed to look like a circle. And this one's pi over 6 from here to here. So pi over 3 is the bigger one, pi over 6 is the smaller one. So that's z square root. So this is z, and that one's square root of z. Where's the other one? So I got to figure that out. So this one here is CIS pi over 6. So that's one of the answers. So this is one of my answers. I'm going to box it. There's always two square roots. So how do I find the other? I'm going to use the same trick that I did over here. So the same trick that we did here, what was the trick that we did to begin with? We took the angle 0 and we added 2 pi to it, and we get the same angle. It's coterminal. Right, so, and then what we did was we took the 2 pi version and divided that by 2 to find its opposite, or the negative. Look at the original. The original is where? Up here. So the original z is 1 CIS pi over 3. So what we want to do, and I don't even need the 1. If it lets me erase it, there we go. What I'm going to do is I'm going to add pi over, or not pi over 2 pi to that. So I want to rotate it again a full circle from there to get an equivalent that's coterminal. So CIS pi over 3. So pi over 3 is the same thing as maybe what else? So I'd like to take pi over 3 and rotate it a full circle from there. So if I add a full circle to pi over 3, what's a full circle in terms of pi over 3? 6 pi over 3? So I'm going to add pi over 3 and 6 pi over 3, and you get 7 pi over 3. It's a weird 7. That's also a weird 7, but whatever. Actually, no, not whatever. I'll try to fix it. I don't like my 7s today, but whatever. So 7 pi over 3 is the same thing as pi over 3 with regards to the CIS function, the cosine I sine function. So I'm going to steal that. I'm going to go over here. So I'm going to take the square root of z, which we can also rewrite it as square root of 1 CIS. In this case, it's going to be 1/2 of the new angle that we found, 7 pi over 3. 7 pi over 3 is functionally the same thing as pi over 3 because it's periodic, or the CIS function is periodic. Every full circle, it returns to the same value. So I want 1/2 of that. So the square root of 1 is 1, and I don't need to write the 1. CIS, the 1/2 times 7 pi over 3, the 2 and the 3 multiplied with 6, so 7 pi over 6. And this is the other one. I'm going to box that because that's my answer as well. So where's 7 pi over 6? If you remember where 7 pi over 6 is at, it's 30 degrees past 180. It's actually a literal extension of this line, this way. So this is pi over 3 this way. Or if I take the whole way through, that's 7 pi over 3. And wherever 1 is at, let's say 1 is here. This is also the other square root of z. So let me write out what these things are in rectangular form. So in rectangular form, let me put rect on there, rectangular. Let's see, CIS pi over 3 is equal to, we said earlier was 1/2 plus, no, it's not 1/2. If we're talking about pi over 3. It's supposed to be pi over 6, my bad. Very sorry about that. So pi over 6. Because cosine of pi over 3 is 1/2, so that's where I was getting confused. The answer is pi over 6. The other answer is 7 pi over 6. So for 7 pi over 6, that's square root of 3 over 2 plus I times 1/2, or 1/2 I. But you could probably write the I second. What's the other one? CIS 7 pi over 6, and that's in the third quadrant. So third quadrant, you would have negative square root of 3 over 2 minus 1/2 I. So if you remember, in the third quadrant, the x-coordinates are exactly the same because it's a circle. Circles are symmetric, but you negate the x and y coordinates is how you play around with the unit circle. So second, third, fourth quadrants, literally the same x and y coordinates for the reference angle. The only difference is the negative signs depending on the quadrant that you're in. Third quadrant, both of them are negative. So I just copy those down and I negate them. So what's the obvious thing here? You're going to get mad at me because this is a square root. What's the difference between these two? The only difference between these two is a negative sign. So, however, there is a geometrical reason for that. So number one, square roots. Square roots are always a plus or a minus. That also gets extended into the complex plane. We didn't know that for what's it called? Complex numbers. So for a complex number, something that's purely complex, if you take its square root, it's going to be two numbers that are negatives of each other. So really the hard work is finding one of them, and then you just negate the other to find the other. So it actually works out the same as in real number land or on the real number line. The two square roots are just negatives of each other, literally just negatives of each other. So what's the geometrical interpretation of it? They're separated by one angle. How far apart are they angularly, the negative and the positive? 180 degrees. So they are separated by 180 degrees. So let me also take this further. Another geometrical truth about these things. They lie on a circle, the same circle with the same radius, because they're supposed to have the same modulus. So that's supposed to be a circle, but so just think that's a circle. Which I could fix that by erasing the bottom. So it's supposed to be a circle. Let's see if I can make that a little bit less ugly. So that's not that bad. So they're both on the same circle, and they happen to be angularly equidistant from each other, 180 on one side, 180 on the other side. So they're going to be symmetrically placed along a circle from each other. So in this case, 180 degrees apart. So you take the full circle, which is 360 degrees or 2 pi, divide that by 2 because there are two square roots. You find one of them, and the other one is on the other side, halfway through. So that's how you take square roots, and that's the way you're going to think of square roots. Square roots lie on the same circle, and they are 180 degrees apart. So there's our first major lesson when it comes to taking roots of complex numbers. So the reason why I wanted to go through all of that is to be comfortable now with this one. Because this one, if you didn't know all that stuff, well, I guess I could have gone to the same spiel with the third roots, but it's easier to think of square roots at first. So we'll look at part C, which I call that part C. That's just example 2. Find the 3 cube roots. So they're already telling you there are 3 cube roots of -8. So let's find the first cube root of 8. So then I want to take the cube root on both sides. So just take the normal algebraic cube root of -8. So -8 cube root. So cube root of z. Whoops, no, sorry. That was throwing me off. So if we have z cubed is equal to -8, you cube root both sides and you get z, just z. No cube root on that side. You get a cube root on this side. Now that was the reason that was throwing me off, because it was wrong. So we're only taking the cube root on both sides once, and you get a cube root on the right-hand side, not on the left-hand side. What's the cube root of negative 8? Well, it's the number that when I multiply it with itself a total of 3 times, I get negative 8. Negative 2. Negative 2 times negative 2 times negative 2 is negative 8. So we get negative 2. So you can try doing that to find one of them right away, and then do the geometry. So what's the other way? This is the same thing as positive 8 with an angle of how much? It's a negative number, 180 degrees. So negative 8 is just 8, positive, rotated 100 degrees. That's the way I think of negative numbers. Negative numbers are a rotation 180 degrees from their positive counterpart. So negative 8 is just positive 8, but rotated 180 degrees. So it's the equilibrant of 8. You can think of it that way, if you want to think of it as a vector. So it's just the opposite, the equilibrant of positive 8. So 8. So negative 2 is one of the answers, which I'm going to box, by the way. Negative 2 is one of the answers. And they're going to want those in rectangular form. That's in rectangular form. So how do I find the others? You take negative 8, which is the same thing as positive 8, angle 180. And we're going to add 360 to that. So key thing, you add 360 to the original, not the first root that we found. We're going to do that to the original. Original. You add 360 to that one. So what's 360 plus 180? That's 540. So then we can think of negative 8 as 8 with an angle of 540 degrees. So literally, if it were 180, we add another 360 to that. And that's 540. It's the same exact spot. Not at that negative 2 place. It's at negative 8. But negative 8 and negative 2 are on the same part, on the same negative x-axis. So then what do we do? If I wanted to find what that one's going to be, so how do I find the next root? Well, I got to go to the rule. So the rule says, and here's the graphical representation for square roots. Here's the rule. You take the cube root of the modulus, and then you divide the angle by the number of the root. So how big the root is. In this case, it's a third root or a cube root. You're dividing by 3. So let's go back to it. So 8 is going to get cube rooted. So cube root of negative 8 is also the same thing as the cube root, and that's cube. Keep forgetting to write the 3 level. So cube of 8, and we're going to divide the angle 540 by 3. I don't know what's 540 divided by 3. Crap. So hold up. Calculator. This is embarrassing. 540 divided by 3. 180. 540 when you divide that by 3. Oh, it's because, oh, yeah, I see how that works. So this is 180, another 180, and then another 180. That's 3 180s. And I'm back where I started. So then I have to fix that 540. So this happens a lot. It depends on where you start. There's like a cyclical nature going on, and we just started at the wrong place. So 540, so that's going to equal to 540. 540 is a bad starting place, so I'm going to add another 360. So if you see that and you get stuck, just add another 360 to 540. So 360 and 540 added together, 900. So we'll start off with 900 then. So 540 is a bad number to start with. 900. And we're going to divide that by 3. And what is 900 divided by 3? 300. So our next angle that I'm going to draw is 300 degrees. And maybe I'm going to go ahead and delete this angle rotation. So cube root of 8 is 2, angle 300. That's another one. So where's 300? 300 is along the same circle. It has to have a radius or a modulus of 2. So we're going to draw a circle with a radius of 2. To the best of my ability, though, because I suck at drawing circles. And that one's not so bad. So on that circle, we're talking about 300 degrees. We have 2 180, 2 300. Let's find another. So what I'm probably going to do is, yeah, just keep on going. So we're going to take that 900. So we got 900 this way. And I'm going to take the 900 and add another 360, which that's going to give me a very large angle. 360 plus that, that's 1260. And that's got to get, see, 1260 is really large. I got to find out where that's at. But anyway, 1260, you have to divide that by 3. So 1260 divided by 3 is 420 degrees. So then the next answer, it's going to be on the same circle with a radius of 2, so I'm guaranteed the modulus is 2, with an angle of 420 degrees. Now 420 degrees is not between 0 and 360, so I'm going to have to scale that back. So that way it's between 360 and 0. So what you do is you subtract 360 from that. So 420 minus 360, oops, 420 minus, not subtract or divided, 60 degrees. So that's 2, 60 degrees. Where's 60 degrees? 60 degrees is here. So that's 2, 60 degrees. And we're doing this kind of slow because we want to make sure that we know exactly where all these numbers are coming from. So that's actually it. This is the geometrical representation of the cube roots of -8. Where's -8? -8, if that's -2, -8's all the way the hell over here. So let's say this is -8. You find one of them by cube rooting its modulus. -8, the cube root of -8 is -2. So you find one of them. And -2 is 2 away from 0, the origin. So that means you're going to draw a circle with a radius of 2 because it's 2 away distance-wise. So you draw a circle. You know where one of them is at. It's at 180 degrees. So then what's the other thing? Or what else do we need to know to figure out the others? So this was 60 degrees. So look at those numbers, 180, 30, and 60. How far apart are each of those from each other? So take a look at that. So how far apart are each of these away from each other? They're all 120 degrees away from each other. All of them are 120 degrees away from each other. What's the significance? So this circle got cut into 3 pieces. 1, 2, 3. And these are all 120. That happened here with the square root circle. So we had 2 square roots. The circle had a radius of 8, which we were zoomed out a lot because 64 was a big number. And both of those were 180 degrees apart. It cut the circle into 2 equal-sized pieces, 2 half circles. Same thing with this one. This circle got cut into 2 halves. This half and then this half. So you had 180 degrees apart. Now, if this is a third root, the third root will cut the circle into 3 equal-sized pieces. So the third root, it's a power or a level of 3 for the root. So that means the circle gets cut into 3 equal-sized pieces. So 3 equal-sized pieces, 120 degrees. So shortcut. So like I said earlier, I wouldn't do this procedure every single time because I know the geometrical shortcut. What's the geometrical shortcut? Take the cube root of the modulus of that number. So find what the modulus is. -8 has a modulus of 8. Take the cube root of that thing, and you would get a cube root of -2, and that's one of them. Then what I do is I'm going to keep on adding 120 degrees over and over and over until I find all 3 of them, because 120 degrees is 360 degrees divided by 3. So you're going to take the circle, 360, and divide it by the level of the root, or the number of the root. In this case, cube root divided by 3. So here's a perfect example of the geometric beauty that I was referring to back in 8.5. Complex numbers have a geometrical nature to them that are very, very intuitive. And it makes it a lot more fun to study this stuff. Because it does make for a bunch of, so if you study the calculus of complex numbers, calculus of real numbers was ugly. And if you can wrap your mind around all that stuff, those formulas are kind of unintuitive. They become a lot prettier when you're doing complex calculus. That's interesting stuff in my opinion. So we'll move on. So this actually, and before we move on though, this actually can be extended to all level roots, or natural number roots. And that's what this theorem is about. This is really elaborate, but this is like a programming way to find all of them. So this is a way to set up on a computer how to find all roots. But the idea is you're going to add to the original angle 360 a bunch of times. That's what that is. And you're going to divide the result by the level of the root, the nth root. And that's how you're going to find that. And the counter on k is going to go from 1 or 0 all the way to n minus 1. So if n was 5, this stops at 4. If n was 7, that's going to stop at 6 and keeps on going. So in this case, n was 3, so that's going to stop at 2. So you go 0, 1, and then 2. And there's going to be 3 total roots. So it's a procedure, and I'm not going to hold you guys to that procedure. I'm going to hold you guys to I'm going to expect out of you guys the geometrical procedure. So think of them as on the same circle, separated by an equal angle apart. So they're an equal angle apart from each other. So you take 360, you divide it by whatever the root is, and that's how far apart those roots are going to be. So it's an easy way to think of it. So we're going to try to think of number 3 that way, and it's going to make it a lot easier. So other than that, if I had never taught you any of that, then you'd get stuck on this problem. How would I find all 4 roots of this number? Negative 128 minus 128i squared root of 3. It looks like a beast of a problem, but it's super easy if you think of it geometrically. So geometrically, we have it in rectangular form, and I'd like that in polar form to make any sense out of it, because I can't make sense out of that in rectangular form. So z, we'll say, and I'm not going to write it in red, we'll say z is equal to negative 128 minus 128 I squared root of 3. You take away the I in your mind, so forget about I. So I'm going to write the I out here. So negative, and then I, 128 squared root of 3. And those are the x and y components, or x and y coordinates, if you want to think of them that way. Find r, using the formula, square root x squared plus y squared. So then what's x? X is negative 128, square that. What is y? Negative 128 squared root of 3. That you can definitely see. Square that. And you get, that's going to be gross, 128 squared. I am not squaring the 128. And then plus 3, 128 squared. Where'd that 3 come from? So you distribute the power of 2 into all 3 of these things, the negative, the 128, and the square root of 3. Negative becomes a positive. That just disappears. 128 squared, leave it as 128 squared because that's going to be a very large number. Square root of 3 squared is 3, which is why there's a 3 in the front. So what happens if I combine these two? 128 squared plus 3, 128 squared. 4, 128 squared. It is beneficial to think algebraically. And if you're not good at the algebra, that's going to be kind of hard. So what next? The 4 comes out as a 2. 2 square root of 128 squared. That's the reason why I left it as 128 squared, because it's going to get square rooted anyway. 2 times 128 is the answer, basically. Well, what's 2 times 128? 256. So there's where the 256 came from. That's the harder way, though, in my opinion. Because I'm a pro at using the unit circle, I just, what's it called? I factored in a 1/2. And in order to factor in a 1/2, you got to multiply the rest of it by 2. So I multiplied the inside by 1/2. I multiplied the outside by 2 to balance it, basically, is what I did in my head. And why did I want the 1/2 and the square root, or why did I want the 2? Because I noticed that 1/2 and square root of 3 over 2, those are special numbers, special angle values. So that's the reasoning behind there. So I'm going to erase all of this. It's in the notes, it's in the video. Hopefully in your notes now. And let's erase. Okay, I need that space for the geometrical reasoning. So I'm going to draw a circle, or the best circle that I can. What's the radius of that circle, if you think of that as a circle? Well, I don't have the radius just yet. I have to take the square root, or fourth root, right? So they want the fourth root. I want fourth root of z. And the very first fourth root of z I'm going to find, that is fourth root of 256, which, by the way, fourth root of 256, whatever that number is, that's going to be the radius of the circle that I drew out there. And then times CIS of 240 divided by 4. Why divided by 4? Because we're talking about a fourth root. So that number is what you're going to divide the angle by. And that's going to give me the fourth root of that number. So let's see, fourth root of 256, I'm stalling. What's 256? After a fourth root. So 256, and I'm going to raise that on my calculator to 1/4 power. Don't forget, a fourth root of, let's call that x, is going to equal to x to the 1/4 power. So if you're doing this in a calculator, whether it's Desmos or you have your own calculator at home, an 84, Inspire, whatever, it's the number raised to the 1 over 4 power. And I'm getting 4. So let me erase that. This is equal to 4 CIS. What's 240 divided by 4? Is that 60? 6 times 4 is 24. So yeah, you add an extra 0 and you get 60 and 240. Okay, so that's the first number I'm going to draw. So 60 degrees, we'll say, is here. So that's 4 and 60. And that's 1/4 of the answer. There are 3 more. This is the hard work, finding the 1. The other 3 are super easy. How do I find the other 3? The other 3 are going to be on the circle an equal distance away from each other. So all 4 of those are going to be in the same angle apart from each other. So you're going to take 360, which is the full circle, divide that by 4. What's 360 divided by 4? 90 degrees. So what that means is, if I keep on adding 90 degrees to that 60-degree angle, I'm going to find more roots. So then, that's going to look like this, by the way, because these are right angles, and like this. And there we are. We're done. Well, almost. I just got to say what those are. 4, 150, because 60 plus 90 is 150. 4, 240, because 150 plus 90 is 240. 4, 330, because 240 plus 90 is 330. And we're done. That's literally it. Except, they're jerks. What do they want? They want them in rectangular form. The math is done, and I hope you understand this math. It's super easy math in my opinion. So the hard part out of all of this is finding the 1, the main 1, the principal root. So you do that using this formula. And if they gave that to you in rectangular form from the beginning, then you use r CIS theta, where r is square root x squared plus y squared. Theta is the inverse tangent of y over x, is what you would do. So let's go back to it. We're almost done. So my answers, 4 with an angle of 60 degrees is 4 CIS 60. What's CIS 60? Cosine 60 plus I sine 60. Unit circle. At this point, I'm hoping you remember how to get all this stuff done in your head. So 4 cosine 60, 1/2. I sine 60, square root of 3 over 2 times I. So 2 plus 2 square root of 3 times I, 2I square root of 3. That's one of them. Let me double check because I tend to make mistakes. Cosine of 60 is 1/2. Sine of 60 is square root of 3 over 2. You multiply 4 into both. 1/2 times 4 is 2. You multiply 4 into square root of 3 over 2. The 4 over 2 reduced to 2. So 2I square root of 3. That looks fine to me. Next one. 4, 150. So that's going to be 4 cosine 150 plus I sine 150. Unit circle. Cosine and sine of 150. So it's 4 negative square root of 3 over 2 plus I times 1/2. Negative 2 square root of 3 plus 2I. Double check. 150 is 30 degrees off of 180, so that's a 30-degree reference angle. So cosine is square root of 3 over 2, sine is 1/2, except cosine is negative because it's in quadrant 2. So yeah, that's fine. You distribute the 4, and yeah, that looks fine. So those are 2. Let's do 2 more. 4, 240. 4 cosine 240 plus I sine 240. 4 times, think of that one, negative 1/2 minus I square root of 3 over 2. Check your unit circle. 240 degrees. Cosine 240 is negative 1/2. Sine of 240, negative square root of 3 over 2. And the way that I can think of this, because those, so think of it this way. The first one that we found was this one. And the third one that we're finding is this one, which is 180 degrees off. So that's literally negative of the first one. So compare that with the previous one. Well, let's simplify. That's negative 2 minus 2I squared root of 3 and that one should match the first one by a negative sign. They should. So for fourth roots, it's kind of easy. You just find two of them and you negate both of those to find the other two. That's another geometrical exploit, and if you know it that way, that's really good because you've mastered this then. One more. 4 angles 330. So then you look at this one, because we're talking about 180 degrees apart. This is positive 2 square root of 3 minus 2i. But you can check 4 cosine 330 plus I sine 330. And you could double check. You look at your unit circle, or maybe don't look at your unit circle. Maybe this is easier than looking at a unit circle. That is positive square root of 3 over 2, negative 1/2. You distribute, and you get 2 square root of 3, which is positive, and then minus 2i, which is exactly the same thing, yeah. So all 4 answers boxed. Let me zoom out. There's the work for example 3. So same idea. So we're talking about a fourth root, so there's going to be 4 answers, and they're going to be 90 degrees apart because 90 degrees times 4 is 360 degrees. That's the reason why. So what you do is you find the modulus, which in this case is 4. So that means the radius of the circle that we're talking about is 4. And then you got to find the original angle. So then you got to find the angle of the original number, and then divide that angle by 4, and that's going to give you one of the fourth roots. Once you found that one, which is the hard work, finding the one is the hard work, then you add 90 degrees over and over and over until you get them all. And then, because they're jerks, they asked for them in rectangular form. And that's basically going to be it for this section. So, for example 4, I'm not going to go over because it's the same thing. Find the solutions of x to the 6th plus I equals to 0, which maybe I do want to go over that one. Maybe at just the beginning. X to the 6th plus I is equal to 0, and they want you to find the solutions. What does that mean? So if I want to find the solutions, it's really x to the 6th is equal to I. So what they want is x equals to the 6th root of I. What they're really talking about is finding all of the 6 roots of I. So they want all 6th roots of I. So the first thing you got to know is that I is the same thing as, and this is interesting, what is I? So I don't know if you're already bored out of your mind or if this is something that's actually interesting to you. I is nothing special. I is nothing but the number 1 with what angle? 90 degrees. So I is literally just a 90 degree rotation of the number 1. So you take the number 1 and you rotate it 90 degrees, which you understand that now, so you can consider yourself a nerd. So the number I is literally just the number 1 rotated 90 degrees. That's it. You rotate I 90 more degrees. So 1 I. That's a rotation. They're on the same circle, by the way. You rotate that another 90 degrees. Negative 1. Rotate it again, negative 90 degrees. Negative I. Rotate that again, 90 degrees. 1. Rotate again, and it keeps on going. It's a cycle. This is a picture, a visual of the cycle of I to the nth power. You all remember that? I to the first is I. I squared, negative 1. That's a definition, by the way. I cubed, negative I. I to the 4th, 1. I to the 5th, I. And it keeps on going in a cycle. This is a vertical list of the cycle. Here is that geometrically. So remember, raising to a power is just a rotation. And if it has a modulus of 1 or a distance of 1, or if it's on the unit circle, it's just going to keep on rotating on that unit circle. So there is a visualization of taking I to a power. It just rotates 90 degrees. That's all it does. So look at these. These are all 90 degrees apart. That's 90 degree difference, 90 degree here, 90 degrees here, 90 degrees here. So now you understand that, hopefully. So that's kind of cool stuff, in my opinion. But I'm not going to do this one. So it's 90 degrees. I could do this a little bit. So then the first 6th root of I is 1 with 90 divided by 6. What's 90 divided by 6, crap? So 90 divided by 6 is 15 degrees. So then your first answer is the number 1 rotated 50 degrees. And then from there, how far are we going to be rotating? You take 360 and you divide that by 6. So 360 divided by 6 is 60. So you keep on adding 60. So all of these numbers are 60 degrees apart, so that we are guaranteed 6 of them total. And I won't finish that, so I'm going to stop there, because that's all we really need to know. I'm going to have you play around with that idea, but in the homework. So we'll stop here for 8, 6.